Welcome to Quantum Curious, and in today's video, I'm going to discuss the very uh, weird property of the particles that arises from the quantum field. And this property is very well discussed throughout the history of the quantum theory, and still there is a lot of debate going on in the scientific community over uh, all the world uh, due to this weird property and that outlandish behavior that particles uh, show at the microscopic level. So this property is called entanglement, and you might have heard about entanglement in general in some public talk or some kind of a video in at YouTube or at TV channel or at uh, a program that have invited some scientist that is very famous and explaining uh, the entanglement, and that is the weird property of the particles in a popular science language. So today I will try to define this property in more mathematical formalism and how it is formally put in quantum information theory. So generally entanglement is the property that is regarded as the non-local correlation between two particles, and it is a very useful quantity or useful property of the particles that has many uses in quantum information protocols like quantum error correction and Shor's algorithm that that introduced the way to factorize the large prime numbers very successfully in a short amount of time the property using this property of particles. So let's dive into this concept of entanglement. So we know that in separable states that are tensor product of uh, two pure states in the case of the bipartite states. But if we have some kind of state that cannot be written as the tensor product of the two pure states that is forming the whole joint states, then we call this kind of states as entangled states. So this is the very precise definition of entanglement in more mathematical formalism. So consider we have uh, not pure states, but we have some kind of mixed states or probabilistic mixture of the states. Then if we could write that probabilistic mixture as tensor product, then we would say that the state is still separable. And if we cannot write that kind of probabilistic mixture for a given probability distribution for a mixed state, then we will say that we have an entangled state. So let's try to clear or understand the concept more efficiently through the examples. So consider we have a pure state, and we could see that from uh, first sight, it is looking like an entangled state. But if if we could stare more deeply and more attentively, we could see that if we could factorize that uh, that qubit in B subsystem out of this in both the cases. So if we factorize that B qubit in state one, out of this, we could write it as this. And we could say that it is a separable state, not entangled state, as we have seen in previous lectures as the PR that was called as maximally entangled state. And we could see that it is just a pure state as the superposition of 0 and 1. And it is the balanced superposition of 0 and 1. And we could see that the given state is just the tensor product of one plus state in Hadamard cases and one state in standard cases. So this was the the separable states, not the entangled states. So the next state is the probabilistic mixture or mixed state, and we could see that it is also a separable state because the uh, we could write the state associated with the system A and system B with the help of a tensor product, and it is a probabilistic mixture and a separable state. So we have seen that the CQ state uh, that are the classical quantum states, as they are composed of a classical part and a quantum part, and written in they are usually written in the form of the tensor product, and they are uh, separable states, not the entangled states. So all the classical quantum states are separable states. So you might have noticed in the previous example that there's some kind of correlation between the two states in the probabilistic mixture. So, for example, if we calculate the zero state uh, or A state uh, in some kind of standard basis, we would get always one state in that case with some probability distribution. And similarly for the Hadamard basis. So that kind of correlation is usually regarded as the classical correlation because it is different from superposition, and you will see that how it is much different from the quantum correlation, and it is much weaker and could be easily stimulated through some kind of functions. And it is still correlated, but there is a difference between quantum correlation and classical correlations. We will see that in just a moment. So the next state is the most famous state, and it is regarded as the maximally entangled state in the two-qubit case, and it is called the EPR state. And we could see that we cannot factorize anything out of it from the part A of the system A or system B, and it is called the EPR state. And symmetrically, we could write the same state in any basis, and it is written in that case for in the Hadamard basis. So this state shows the behavior of correlation much stronger than the classical correlations, and we will see in a moment with the help of example. So consider we have again the probabilistic mixture of states A and B that are written in the standard basis, and we have the pure state of the EPR pair. So writing that pure state in the form of a density matrix for EPR pair, we can write this as this. So let's measure that both states in the standard basis. So if we measure these states in standard basis, we will get same kind of correlation. So for example, if we measure the state for AB in states in standard basis, and if we get result 0 in A, we are sure that we are going to get 0 in B. And similarly, if we get 0 here in EPR case, so we are going to get 0 in B uh, as previously uh, for the row AB. And similarly, if we get the result 1 in A for row AB, we are guaranteed to get the result 1 for system B. And similarly for the EPR state. So in the standard basis, both are showing the same kind of relations and correlations between the two qubits, and we will see that how they will differ for the measurement in different bases, like Hadamard basis. So consider if we measure both qubits in Hadamard basis, and we have operator these. So let's say we are going to measure the state for AB in Hadamard basis, and we are conditioning that the system A will give the outcome plus in that case. So the post measurement state, we can calculate this as this, and we could see that in that case, the state P is going to collapse into a maximally mixed state, not the plus state, not the negative state, but the maximally mixed state. And in that case, the, uh, we could see that the system A and B are not that much correlated. And this is different from the measurement that we saw earlier in the standard process. So let's see if we if we do the measurement in further matrices for the EPR pair. So what we are going to get in that case. So consider we again condition that we are going to get the outcome plus in the system A for the EPR where uh, we are going to calculate the post measurement state, uh, and we could see that after calculation we could see that the state are going to be correlated. So, for example, if we calculate if we get the outcome A for plus state, then we are going to have plus state for B. So both outcomes are correlated with each other, and this is the beauty of entanglement. And we could see that this is quite different from the state that we saw in the case of the row AB, that is just the maximally that that is just the mixed state and just a probabilistic mixture of 0 and 1. So we could see that the quantum correlations are quite different and much stronger in the sense that they are not dependent on the measurement or the measurement basis. They're going to give the correlated results, and these correlations are much stronger than the classical case. So that's all for it. So hope you have enjoyed the lecture. And if you like the video, don't forget to like, share, and subscribe to Quantum Curious.